Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. The year 1957 marked humanity's first tentative steps into the cosmos, but what the world witnessed was merely the tip of an iceberg. While Sputnik 1 orbited Earth every 96 minutes, broadcasting its simple radio signals to amateur operators worldwide, a shadow war was already brewing 400 kilometers above our heads. The Cold War had found a new battlefield, one where the stakes were measured not in territorial gains, but in orbital supremacy. Behind the public spectacle of space exploration lay a labyrinth of classified programs that would reshape military strategy for decades. The United States and Soviet Union weren't just racing to plant flags on the moon, they were developing capabilities that could determine the outcome of terrestrial conflicts. Reconnaissance satellites became the new high ground. Communication networks spanning continents replaced traditional intelligence channels, and weapons platforms in space transformed from science fiction into classified reality. The Corona program, America's first photo reconnaissance satellite initiative, began in 1959 under the cover story of scientific research. Designated publicly as Discoverer, these satellites carried cameras capable of resolving objects as small as 3 meters across from altitudes exceeding 150 kilometers. Between 1960 and 1972, Corona missions captured over 800,000 images of Soviet and Chinese territory, providing intelligence that no ground-based spy network could match. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. Simultaneously, the Soviet Union pursued its own clandestine orbital operations. The Cosmos program served as an umbrella designation for hundreds of military satellites, their true purposes hidden beneath generic scientific descriptions. Cosmos 1, launched in 1962, was actually Zenit 2, a reconnaissance satellite designed to photograph NASA facilities and U.S. military installations. This dual-use approach allowed both superpowers to maintain plausible deniability while advancing their strategic space capabilities. The Manned Orbiting Laboratory, or MOL, represented America's most ambitious military space program. Conceived in 1963, this project aimed to place two-person crews in orbit for up to 30 days, conducting surveillance and testing military space technologies. The program's estimated cost reached $4 billion in 1970s. Currency, equivalent to approximately $28 billion today. Despite never achieving operational status, MOL drove innovations in life support systems, orbital maneuvering, and reconnaissance technology that would influence space programs for generations. Soviet military cosmonauts trained alongside their civilian counterparts, preparing for missions that remained classified until the collapse of the USSR. The Almaz program developed military space stations capable of hosting crews for extended periods while conducting Earth observation and potential anti-satellite operations. These stations, launched under the civilian Salyut designation, carried sophisticated cameras and even a 23mm cannon, the only firearm ever deployed in space. The implications extended beyond mere espionage. Both nations recognized that space-based assets would become critical infrastructure, vulnerable to attack but capable of providing decisive advantages. Early warning satellites could detect intercontinental ballistic missile launches within minutes, while communication satellites enabled secure command and control networks spanning global distances. The race wasn't just about reaching space, it was about controlling it. As we delve deeper into these hidden programs, we'll uncover technologies that pushed the boundaries of what was thought possible, missions that remained secret for decades, and the brilliant minds who transformed science fiction concepts into orbital reality. The Cold War's space programs weren't just about national prestige, they were about survival in an age when the high ground meant everything, and everything meant control of the ultimate frontier above our heads. While the world marveled at astronauts floating weightlessly through space, America's most valuable space assets remained invisible to public view. The Corona Reconnaissance Satellite Program represented a technological leap that transformed intelligence gathering from human networks on the ground to automated systems orbiting at 17,500 miles per hour. These mechanical spies fundamentally altered how nations understood their adversaries' capabilities and intentions. Corona's development began in 1956, emerging from a collaboration between the Central Intelligence Agency and the U.S. Air Force. The program's technical challenges seemed insurmountable. Cameras had to function in the vacuum of space. Film had to survive temperature extremes ranging from minus 150 degrees Celsius to positive 120 degrees Celsius, and recovery systems had to snatch film capsules from mid-air as they plummeted toward Earth at supersonic speeds. The camera systems aboard Corona satellites pushed photographic technology to its limits. The KH-4 camera, introduced in 1963, featured a focal length of 610 millimeters and could capture images across a swath 165 kilometers wide. Film magazines contained over 9,000 feet of specially formulated Eastman Kodak film, capable of recording approximately 16,000 individual frames during a typical mission lasting 4 to 7 days. Recovery operations required precision that bordered on the miraculous. After completing their photographic missions, satellites would eject film canisters equipped with heat shields and parachute systems. C-130 aircraft, trailing specialized cables and hooks, would snare the descending capsules at altitudes between 3,000 and 4,000 meters. This mid-air recovery technique, known as aerial fishing, achieved a success rate exceeding 90% after initial operational challenges were resolved. The intelligence value of Corona imagery proved extraordinary. The first successful mission, Corona 9 in August 1960, captured more photographic intelligence of the Soviet Union than all previous U-2 spy plane flights combined. These images revealed the true scope of Soviet missile programs, confirming that the feared missile gap was actually in America's favor. Premier Nikita Khrushchev's claims of mass-producing intercontinental ballistic missiles were exposed as strategic deception. Gambit satellites, operational from 1963 to 1984, provided even higher resolution imagery. The KH-7 and KH-8 camera systems achieved ground resolution approaching 30 centimeters, enabling analysts to distinguish individual vehicles, identify aircraft types, and assess construction progress at military facilities. These satellites operated from lower orbits, typically between 150 and 300 kilometers altitude, sacrificing orbital longevity for image quality. The Hexagon program, nicknamed Big Bird, represented the pinnacle of film-based reconnaissance technology. These massive satellites, weighing over 13,000 kilograms, carried cameras with unprecedented coverage capabilities. A single Hexagon mission could photograph an area equivalent to half the continental United States with resolution sufficient to identify objects as small as 60 centimeters across. Between 1971 and 1986, 20 Hexagon satellites captured over 877,000 images. Technical innovations developed for these programs extended far beyond photography. Attitude control systems maintained satellite orientation within hundredths of a degree, essential for preventing image blur during long exposures. Thermal management systems protected sensitive electronics and film from the extreme temperature variations encountered. In orbit, communication systems enabled ground controllers to adjust mission parameters, optimize coverage areas, and coordinate recovery operations. The transition from film return to digital transmission revolutionized satellite reconnaissance. The KH-11 series, first launched in 1976, transmitted images electronically through relay satellites, providing near real-time intelligence to decision-makers. This capability proved crucial during international crises, when waiting days or weeks for film recovery could render intelligence obsolete. By the program's conclusion, American reconnaissance satellites had fundamentally transformed strategic intelligence. These orbital platforms provided continuous monitoring of Soviet military activities, verified arms control compliance, and supported military operations worldwide. The technology developed for these classified programs later enabled civilian Earth observation satellites, weather monitoring systems, and commercial imaging services that we rely on today. Behind the Iron Curtain, Soviet engineers were developing their own orbital espionage capabilities with characteristic ingenuity and resourcefulness. While American reconnaissance satellites relied on sophisticated film return systems, Soviet designers pursued different technological approaches that reflected their nation's industrial strengths and strategic priorities. The result was a constellation of surveillance satellites that, while less publicized than their American counterparts, proved equally effective at gathering critical intelligence. The Zenit program began development in 1958, just 1 year after Sputnik's historic flight. Chief designer Sergei Korolev adapted his R-7 missile technology to create a reconnaissance platform that could photograph military installations across the United States and its allies. The first successful Zenit mission, designated Cosmos, 4 launched in April 1962 and marked the Soviet Union's entry into space-based intelligence gathering. Zenit satellites employed a fundamentally different recovery approach than American systems. Instead of ejecting film capsules for mid-air capture, the entire satellite would return to Earth after completing its mission. This design decision reflected Soviet confidence in their re-entry technology, developed through the Luna and Vostok programs. The SA-20 recovery module, weighing approximately 2,700 kilograms, would separate from the service module and descend under parachutes to predetermined landing zones in Kazakhstan. The photographic systems aboard Zenit satellites demonstrated remarkable capability despite their apparent simplicity. The SA-19 camera, with its focal length of 1,000 millimeters, could achieve ground resolution approaching 2 meters from orbital altitudes of 200 to 400 kilometers. Film capacity exceeded 1,500 individual exposures, covering areas up to 160,000 square kilometers per mission. These specifications enabled comprehensive surveillance of strategic targets, including missile bases, naval facilities, and nuclear installations. Soviet satellite operations benefited from extensive ground-based support networks spanning 11 time zones. Tracking stations from Plesetsk to Kamchatka provided continuous communication coverage, while dedicated recovery teams positioned throughout Central Asia ensured rapid film retrieval. This infrastructure advantage allowed Soviet controllers to maintain precise orbital tracking and optimize photographic opportunities despite the technological limitations of early guidance systems. The Yantar program, introduced in 1974, represented a significant advancement in Soviet reconnaissance technology. These satellites incorporated film return capsules similar to American Corona systems, but with distinctly Soviet engineering solutions. The Yantar 2K variant could operate for extended periods, ejecting multiple film capsules during missions lasting up to 60 days. This capability provided Soviet intelligence services with near-continuous surveillance of critical targets. Perhaps most intriguingly, Soviet designers developed specialized reconnaissance satellites for specific intelligence requirements. The Yantar 4K2, operational from 1979, featured extremely high-resolution cameras capable of achieving ground resolution approaching 30 centimeters. These satellites operated from lower orbits, typically 150 to 200 kilometers altitude, and could maneuver to optimize coverage of high-priority targets. The Cosmos designation served as an effective cover for Soviet military space activities. Between 1962 and 1991, over 2,000 satellites received Cosmos numbers, with hundreds dedicated to reconnaissance missions. This numbering system obscured the true purpose and capabilities of Soviet military satellites, complicating Western intelligence assessments and maintaining operational security around sensitive programs. Soviet electronic intelligence satellites, designated Selena, monitored radio communications and radar emissions across the globe. These platforms, weighing up to 4,000 kilograms, carried sophisticated receivers capable of intercepting military communications, tracking radar, installations and mapping electronic warfare capabilities. The Selena II series, operational from 1975, provided Soviet military planners with comprehensive electronic intelligence that complemented photographic reconnaissance. Manufacturing capabilities within the Soviet Union enabled mass production of reconnaissance satellites using standardized components and proven designs. The Zenit production line delivered over 500 satellites between 1961 and 1994, making it one of the most prolific satellite programs in history. This industrial approach provided sustained intelligence gathering capabilities despite individual satellite limitations. The legacy of Soviet reconnaissance programs extended well beyond the Cold War's conclusion. Technologies developed for military surveillance enabled civilian Earth observation satellites, weather monitoring systems, and scientific research platforms. Russian Federation space agencies continue operating reconnaissance satellites based on Soviet-era designs, demonstrating the enduring value of these pioneering systems. While civilian astronauts captured public imagination with their peaceful missions of exploration, a parallel program was training military personnel for a very different kind of space service. The Manned Orbiting Laboratory, America's most ambitious military space program, aimed to place uniformed personnel in orbit, conducting reconnaissance, surveillance, and experimental operations that pushed the boundaries of what was considered possible in the 1960s. The MOL program emerged in December 1963 from recognition that human operators could provide capabilities beyond those of automated systems. Secretary of Defense Robert McNamara envisioned military astronauts conducting real-time photographic reconnaissance, adjusting camera parameters based on weather conditions, cloud cover, and target priorities. These human operators could distinguish between decoys and genuine military installations, identify camouflaged facilities, and respond to unexpected intelligence opportunities. The technical specifications of MOL were extraordinary for their era. The laboratory measured 14.7 meters in length and 3.05 meters in diameter, providing a pressurized workspace larger than any previous American spacecraft. 2 crew members would live and work in orbit for missions lasting up to 30 days, conducting experiments while operating sophisticated reconnaissance equipment through a modified Gemini spacecraft, serving as their return vehicle. 17. Military astronauts trained for MOL missions between 1965 and 1969. These men, drawn from test pilot programs across all military services, underwent training regimens that combined traditional astronaut preparation with specialized military operations. They learned to operate high-resolution cameras, interpret photographic intelligence, and conduct experiments related to military space applications. Many would later join NASA's astronaut corps, though their MOL experience remained classified for decades. The Soviet Union pursued a parallel path with their Almaz military space station program. Unlike the peaceful scientific image projected by the civilian Salyut program, Almaz stations were designed specifically for military reconnaissance and defense. These facilities, designated orbital piloted stations in Soviet documentation, represented a fundamentally different approach to military space operations. Almaz stations incorporated defensive capabilities that remain unique in space exploration. History. Each station carried a modified R-23 Kartek 23mm cannon, originally developed for aircraft applications but adapted for space combat. This weapon system, capable of firing at 650 rounds per minute, was designed to defend against approaching hostile spacecraft or disable enemy satellites. Ground testing demonstrated the cannon's effectiveness in vacuum conditions, though it was never fired operationally in space. The operational capabilities of Almaz stations exceeded those of contemporary American systems. Crews of 2 to 3 cosmonauts could remain in orbit for extended periods, conducting photographic reconnaissance using high-resolution cameras and electronic intelligence-gathering equipment. The Agate-1 camera system achieved ground resolution approaching 1 meter, while electronic surveillance equipment monitored radio communications and radar emissions across targeted regions. Soviet military cosmonauts underwent training that differed significantly from their civilian counterparts. These officers, drawn primarily from Air Force and Strategic Rocket Forces backgrounds, learned to operate military-specific equipment while maintaining combat readiness in space. Their training included weapons handling, defensive maneuvering, and procedures for conducting military operations in zero-gravity environments. The first Almaz station, launched in April 1973 under the cover designation Salyut. 2. Experienced technical difficulties that prevented crew operations. However, subsequent stations demonstrated remarkable capabilities. Salyut 3, actually Almaz 2, hosted 2 successful crewed missions in 1974, with cosmonauts conducting extensive military reconnaissance operations over strategic targets including American missile bases and naval facilities. Both American and Soviet military space programs pushed technological boundaries in life support, orbital maneuvering, and spacecraft systems. The MOL program developed advanced environmental control systems, waste management technologies, and crew habitability solutions that would later benefit civilian space stations. Similarly, Almaz innovations in automated systems, crew transfer procedures, and long-duration spaceflight contributed to subsequent Soviet space achievements. The cancellation of MOL in June 1969 reflected changing strategic priorities and budget constraints rather than technical failures. Advances in automated reconnaissance satellites, particularly the KH-11 digital imaging systems, provided intelligence capabilities that approached those envisioned for human operators. However, the program's contributions to American space technology and astronaut training proved invaluable for future civilian and military applications. These military space programs demonstrated that human presence in orbit could provide unique capabilities for intelligence gathering, experimentation, and potentially combat operations. Though the Cold War ended before space-based warfare became reality, the technologies and operational concepts developed during this era continue influencing military space planning today. The ultimate militarization of space during the Cold War extended far beyond surveillance and reconnaissance. Both superpowers developed weapons systems designed to function in the vacuum of space, transforming orbital mechanics into ballistics and turning satellites into potential targets or platforms for destruction. These programs pushed the boundaries of physics, engineering, and international law, while creating capabilities that could fundamentally alter the nature of warfare. America's anti-satellite weapons development began with the Bold Orion program. In 1958, this system utilized a B-47 bomber to launch a modified Polaris missile at orbiting targets. The first successful test occurred in October 1959, when Bold Orion intercepted the Explorer 6 satellite at an altitude of 251 kilometers. The missile passed within 6.4 kilometers of its target, demonstrating the feasibility of kinetic anti-satellite attacks. The Program 437 represented America's most sophisticated anti-satellite system during the Cold War era. Based at Johnston Atoll in the Pacific, this system employed Thor intermediate-range ballistic missiles equipped with W-49 nuclear warheads yielding 1.4 megatons. Between 1964 and 1975, Program 437 conducted multiple tests, including the Starfish Prime high-altitude nuclear detonation that created electromagnetic pulse effects observable across the Pacific Ocean. Soviet anti-satellite capabilities developed along different technological pathways. The Cosmos 954 series, beginning operations in 1968, employed co-orbital interception techniques. These satellites would maneuver close to target satellites before detonating conventional warheads designed to destroy or disable enemy spacecraft through fragmentation and electromagnetic effects. The system achieved multiple successful tests against Soviet target satellites, demonstrating operational capability against American reconnaissance assets. Nuclear weapons in space presented unique technical challenges and unprecedented destructive potential. High-altitude detonations created electromagnetic pulse effects that could disable electronic systems across vast areas, while radiation belts generated by nuclear explosions posed long-term hazards to spacecraft and astronauts. The Starfish Prime test in July 1962 disabled multiple satellites, and created artificial radiation belts that persisted for years. The Soviet Union conducted its own high-altitude nuclear tests, including detonations at altitudes exceeding 300 kilometers. These tests, designated Operation K, demonstrated that nuclear weapons could effectively destroy satellites and create electromagnetic effects spanning continental distances. The strategic implications were profound. A single high-altitude nuclear detonation could blind an entire nation's satellite reconnaissance and communication capabilities. Directed energy weapons research emerged as both nations explored alternatives to nuclear anti-satellite systems. The Soviet Terra-3 program, based at Saryshagin Test Facility, developed ground-based lasers capable of damaging satellite sensors and electronics. These systems, operating at megawatt power levels, could potentially blind reconnaissance satellites or interfere with their operations without creating orbital debris or radioactive contamination. American directed energy research included the Mid-Infrared Advanced Chemical Laser Program, which demonstrated the ability to track and illuminate satellites with high-powered laser beams. While not immediately destructive, these systems could damage sensitive optical equipment or solar panels, effectively disabling target satellites. The technology later contributed to the Strategic Defense Initiative's more ambitious laser weapons programs. Space-based weapons platforms represented the ultimate militarization of orbital space. Both nations studied concepts for orbital bombardment systems that could deliver kinetic or nuclear weapons to terrestrial targets within minutes of command authorization. These systems would operate from orbital altitudes, making them difficult to defend against using conventional anti-aircraft or anti-missile systems. The fractional orbital bombardment system, developed by the Soviet Union, demonstrated operational capability to place nuclear warheads in low Earth orbit before deorbiting them onto designated targets. This system could attack targets from unexpected directions, bypassing traditional ballistic missile defense systems and reducing warning times to mere minutes. Several tests between 1967 and 1971 proved the concept's viability. International recognition of space weaponization. Dangers led to the Outer Space Treaty of 1967, which prohibited the placement of weapons of mass destruction in orbit around Earth. However, this treaty did not address conventional weapons, anti-satellite systems, or terrestrial-based weapons targeting space assets. The legal framework remained incomplete, even as military space capabilities continued advancing. The technical legacy of Cold War space weapons programs continues influencing modern military space development. Kinetic interceptors, laser systems, and electronic warfare capabilities against satellites all trace their origins to research conducted during this period. While no space-based weapons became permanently operational, the technologies developed demonstrated that orbital warfare was not merely science fiction, but an achievable military capability with profound strategic implications. The intelligence gathered by orbiting reconnaissance satellites fundamentally transformed how nations understood their adversaries, verified treaty compliance, and made strategic decisions during the Cold War's most dangerous moments. These mechanical spies provided unprecedented insight into military capabilities, industrial capacity, and strategic intentions that human intelligence networks could never achieve. The revolution extended far beyond simple photography to encompass comprehensive analysis of enemy capabilities and behavior patterns. Corona satellite imagery first revealed the true scope of Soviet missile capabilities in 1961, definitively resolving the missile gap controversy that had dominated American political discourse. Intelligence analysts discovered that the Soviet Union possessed far fewer intercontinental ballistic missiles than publicly claimed. Instead of hundreds of operational ICBMs, satellite photography identified fewer than 10 deployed R-7 missiles at Plesetsk and Baikonur. This revelation reshaped American nuclear strategy and defense spending priorities. The Cuban Missile Crisis of October 1962 demonstrated satellite intelligence's critical importance during international confrontations. While U-2 reconnaissance flights provided the initial evidence of Soviet missile deployments in Cuba, Corona satellites captured comprehensive imagery of missile sites, support facilities, and defensive installations across the island. These photographs enabled American analysts to identify specific missile types, estimate operational timelines, and assess Soviet intentions with unprecedented accuracy. Strategic Arms Limitation Treaty negotiations, beginning in 1969, relied heavily on satellite verification capabilities. Both superpowers recognized that meaningful arms control required independent verification of treaty compliance, and reconnaissance satellites provided the technical means to monitor missile deployments, test activities, and production facilities. The concept of national technical means of verification, incorporated into SALT agreements, legitimized satellite reconnaissance while avoiding explicit acknowledgement of classified programs. Satellite intelligence revolutionized understanding of Soviet industrial and military infrastructure. Comprehensive photographic coverage revealed the locations and capabilities of weapons manufacturing facilities, military research installations, and strategic material stockpiles. Analysts could track construction progress at missile bases, estimate production rates at aircraft factories, and identify new weapon systems during development phases. This intelligence enabled more accurate threat assessments and defense planning. The intelligence value extended beyond static installations to include operational activities and behavioral patterns. Satellite imagery captured naval exercises, aircraft deployments, and troop movements that revealed Soviet military doctrine and operational capabilities. Time series analysis of satellite photographs enabled intelligence analysts to identify seasonal patterns, training cycles, and logistical networks that provided insights into enemy planning and intentions. Electronic intelligence satellites transformed understanding of Soviet command and control systems. The Rhyolite and later Magnum satellites, positioned in geosynchronous orbits, intercepted microwave communications, telemetry signals, and radar emissions across vast areas of Soviet territory. This electronic intelligence revealed communication protocols, identified key personnel, and provided early warning of military activities that might indicate preparation for conflict. Intelligence fusion techniques developed during this period combined photographic, electronic, and human intelligence sources to create comprehensive assessments of enemy capabilities. Specialized analysis centers employed hundreds of skilled interpreters who could identify specific aircraft types, estimate facility purposes, and track weapon system developments through careful examination of satellite imagery. These analytical capabilities became force multipliers that transformed raw intelligence into actionable strategic information. The psychological impact of omnipresent surveillance affected Soviet behavior and strategic planning. Knowledge that American satellites could observe activities anywhere within Soviet territory influenced facility construction, camouflage efforts, and operational security measures. This satellite effect modified enemy behavior in ways that often provided additional intelligence value while constraining their freedom of action. Crisis management capabilities improved dramatically as real-time intelligence became available. Through digital transmission satellites, the KH-11 series, operational from 1976, provided near-instantaneous imagery of developing situations worldwide. This capability proved crucial during international crises, when decision-makers required current intelligence to assess threats and plan responses within compressed timeframes. Arms control verification evolved into a sophisticated process combining satellite imagery, electronic intelligence, and on-site inspections. The Intermediate Range Nuclear Forces Treaty of 1987 included detailed verification protocols that relied primarily on satellite monitoring capabilities. Treaty compliance became verifiable through technical means rather than trust, enabling agreements that might otherwise have been impossible during periods of intense superpower rivalry. The democratization of intelligence through satellite systems reduced American dependence on Allied intelligence services and human agents operating in hostile territory. Independent verification capabilities provided confidence in intelligence assessments while reducing risks to human sources. This transformation enabled more aggressive intelligence collection and analysis without compromising personnel or diplomatic relationships. By the Cold War's conclusion, satellite intelligence had become indispensable to national security decision-making, military planning, and international diplomacy. The capabilities developed during this period established foundations for modern intelligence operations and continue influencing how nations monitor compliance with international agreements and assess potential threats in an increasingly complex world. The classified space programs of the Cold War era established technological foundations and operational concepts that continue shaping modern space activities across military, civilian, and commercial sectors. Technologies developed in secrecy for intelligence gathering and military applications eventually enabled global positioning systems, weather forecasting, communications networks, and Earth observation capabilities that billions of people rely upon daily. The transformation from classified military tools to essential public infrastructure represents one of the most significant technology transfers in human history. Global Positioning System satellites trace their origins directly to Cold War military space programs. The precise timing systems, orbital mechanics calculations, and signal processing techniques developed for reconnaissance satellite operations provided essential technologies for GPS constellation design. Navigation accuracy requirements for targeting reconnaissance cameras evolved into positioning capabilities that now enable everything from smartphone maps to precision agriculture and autonomous vehicle navigation. Modern commercial Earth observation companies operate satellites with capabilities that exceed many Cold War reconnaissance systems. Companies like Planet Labs and Maxar Technologies provide imagery with resolution approaching 30 centimeters, available to civilian customers within hours of collection. This democratization of satellite intelligence capabilities represents a fundamental shift from the highly classified, government-controlled reconnaissance systems of the 1960s and 70s. Military space operations today reflect operational concepts pioneered during the Cold War. The United States Space Force, established in 2019, employs organizational structures and mission concepts that originated with classified programs like Corona and Gambit. Modern military satellites provide continuous global surveillance, secure communications, and navigation services that evolved directly from Cold War military space requirements. Anti-satellite weapons development continues based on technologies demonstrated during the Cold War. China's successful destruction of its Fengyun 1C weather satellite in January 2007 employed kinetic interceptor technology similar to American and Soviet systems tested decades earlier. Russia's development of co-orbital anti-satellite systems reflects concepts pioneered by the Cosmos 954 series during the 1970s. Space situational awareness capabilities essential for modern space operations evolved from Cold War satellite tracking requirements. The ability to monitor thousands of active satellites, predict collision risks, and track space debris originated from military needs to understand enemy satellite capabilities and protect friendly space assets. Today's space surveillance network operates facilities and employs techniques developed initially for monitoring Soviet military satellites. Commercial satellite imagery has revolutionized fields ranging from urban planning to environmental monitoring. Using technologies pioneered by classified reconnaissance programs, high-resolution cameras, digital image processing, and automated analysis techniques developed for military intelligence now enable precision agriculture, disaster response, and climate change research. The transition from classified military applications to civilian benefits demonstrates the dual-use nature of space technology. International space law continues grappling with issues first raised by Cold War military space programs. The Outer Space Treaty of 1967 addressed weapons of mass destruction in space, but left conventional weapons and anti-satellite systems largely unregulated. Modern space activities, including commercial satellite constellations and space tourism, operate within legal frameworks established during the Cold War era. Cybersecurity threats against satellite systems represent a modern evolution of electronic warfare concepts developed during the Cold War. Nation-states now employ cyber attacks to disable enemy satellites, steal intelligence, or disrupt communications. Networks. These capabilities trace their conceptual origins to electronic intelligence satellites and communication interception systems deployed decades earlier. Space debris, largely created by anti-satellite weapon tests and satellite failures, poses increasing risks to all space operations. The Kessler syndrome, where cascading collisions create exponentially increasing debris clouds, represents a long-term consequence of Cold War space weapons testing. Managing this debris requires international cooperation and technological solutions that build upon space surveillance capabilities developed for military purposes. Private space companies now perform functions once exclusive to government space programs. SpaceX provides launch services for military satellites, while Planet Labs offers commercial imagery that supplements government intelligence capabilities. This public-private partnership model represents an evolution from the strictly classified, government-controlled space programs of the Cold War era. The technical workforce that developed Cold War space technologies transferred their expertise to civilian space programs after classification restrictions were lifted. Engineers and analysts who worked on Corona satellites contributed to Landsat Earth observation missions, while reconnaissance satellite designers helped develop commercial imaging systems. This knowledge transfer accelerated civilian space technology development and established American leadership in commercial space markets. Contemporary space security challenges require international cooperation mechanisms that didn't exist during the Cold War. Space traffic management, debris mitigation, and crisis communication protocols must function across national boundaries in ways that Cold War classification requirements prevented. Modern space governance requires transparency and cooperation that contrasts sharply with the secrecy that characterized military space programs during superpower competition. The legacy of Cold War secret space programs demonstrates both the potential and perils of military space activities. While these programs produced revolutionary technologies that benefit humanity, they also established precedents for space weaponization and created long-term challenges like orbital debris. As humanity expands its presence in space, the lessons learned from this hidden chapter of the space age continue providing crucial insights for managing the opportunities and risks of our orbital frontier. Understanding this classified history helps us navigate contemporary space challenges with awareness of how military requirements drive technological development, how space capabilities influence international relations, and how the decisions made in secret laboratories and launch facilities decades ago continue shaping our connected, space-dependent world today.